All right.
Very good. So it's a pleasure that Mr. try to blow his course on dark matter.
Okay. So as I promised, the last lecture will be about waves and how we can look for wave dark matter. So we'll be talking about a particular example. So I don't know how long that will last. And if we have time towards the end, I will show you some pictures of like some of the detectors that are running. And if we have some additional time, maybe I will tell you a little bit more about the homework problem, about the clock. Anybody who did the homework? Tried. Okay. Okay, so yeah, like if people know, but like I will go very fast, like even if I cover like the homework, try to show you on the board like what is going on. Yeah, if you have more questions about the homework, you can ask me later, especially the last one. Anyway, okay, so let's get started. So in this lecture, we are going to make a wave detector, right? So, but to start with, let's summarize what we learned yesterday. What we learned yesterday is if I'm looking for a WIM, right? So the way that I can be looking for it is through collision. And the maximum energy I can extract is the mass of the dark matter times the velocity squared, the kinetic energy, which in other words is 10⁻⁶ the mass of the particle. So when we consider waves made of particles that doesn't have a conserved quantum number, then this particle can be absorbed, just like our photon. So in this case, again, like my dark matter is still non-relativistic. So the maximum amount of energy I can extract from each single dark matter particle is basically mass of the particle. Right, so it's 6 order of magnitude bigger, so that's good with absorption. And do the same if we want to do conversion, right? So if I convert a photon into some other particle, then I get all of its energy. Okay. So in the case of the absorption, as we said, most of this energy goes into something like a heat. And in this case of conversion, then all of this energy, let's say, go into a photon at the same frequency. So if I'm looking at this side, I want to do absorption or conversion because I get more of the signal from each dark matter particle. It gives me more energy. On this side, comparing these two, right, a particle can usually be both absorbed and converted. Then we should maybe always try to do conversion because in this case, I get some quanta with a particular energy, which maybe we can distinguish from background much better than if we get heat, right? Everything can heat my detector up. All of this noise can heat the detector up at some level. But if I really want to be looking at photon, let's say of a KeV, X-ray photon, then only radioactivity and cosmic ray can give me that. If I'm looking for optical photon, pretty much the same thing. If I'm looking for a radio photon, of course, I need to worry about thermal noise. But again, there are better ways. If I'm looking for a quanta or a signal at a particular frequency, then signal that is in the form of heat, right? So today we'll be showing you how to do conversion. And as I said, if we can do conversion, we should always try to do that. So does conversion always happen, right? So can I always do conversion? And maybe like a simpler question is, what if I just leave the dark matter in the vacuum, right? So the dark matter is everywhere. Does the dark matter, let's say it's a wave, let me use this dashed line, always convert to a photon in any environment, right? Can this happen, right? The answer should be no, right? Otherwise, the dark matter is all gone. We are left with a bunch of photons, right? But why you cannot do it? Huh? What? There's no symmetry, right? There's no constant quantum number saying that this cannot decay.
For a single photon process, this violates conservation.
Good, okay. So this process violates energy momentum conservation, always. To see that, let me draw a particle on a plot of omega and k, right? So a dark matter particle is non-relativistic, right? So it has a frequency that is much more than the momentum. So in this plot, a dark matter particle lives on this line, and we know the velocity is tiny. So this arrow, maybe let me use a different color. This blue arrow shows you a dark matter particle, right? The photon is relativistic. So it lives on the line cone, right? So omega equals k times c, and we see, say c is 0, so omega equal to k, right? So this is a photon, and this is a dark matter particle. So if I want to do conversion, if I try to convert to this energy, right, then I need some additional momentum that dark matter particle doesn't have. If I want to convert to a photon at this energy, then this momentum, then like you need to dump all of this energy away, right? So with this simple picture, you see like why conversion doesn't happen in vacuum. So how do I make it happen not in vacuum? And that to see that, so this is a momentum space, right? Let's go to position space and see like what does this plot mean in position space. Okay. So in position space, I have amplitude of the wave as a function of time. I have the amplitude of the wave as a function of space, right? So that's my wave. As a function of time, dark matter, the blue thing, is oscillating, right? So it's a harmonic oscillator with a particular frequency, and so this period is 1 over m, right? So this is my dark matter oscillation in time. The photon is doing the same thing. Let's say like a photon of this frequency, right? So in this case, my photon is doing exactly the same thing, right? At the same frequency, here, omega gamma. What about in position space? As a function of x, my photon is a wave exactly the same, right? This is 1 over frequency, or 1 over m. However, the dark matter is a non-relativistic particle. It has the Boyer wavelength, which is very large, right? 1 over mv is very large. So within this small range, it's basically a constant, right? So that's how you see the dark matter and the photon in position space. If I want to do conversion, then basically what I'm computing is the overlap of the wave function, right? I take the wave function of the photon. Let me call A of the photon as a function of x and t. And then I take the wave function of the dark matter, right, as a function of x and t, and I integrate it over space and time, which tells me how likely this conversion is going to happen, right? If the two wave functions look the same, then they can convert into each other. If they are not, then you cannot. So, now you see the problem, right? Because this is a constant, this thing is oscillating. So what I'm computing here is the integral of a cosine kx times 1 dx, and I'm doing like a 0 to infinity integral. And this gives me 0, right? Fourier analysis. So this is how you see that dark matter photon conversion cannot happen in position space, because their wave function look quite different, right? Yeah.
In the picture, the
mass of the dark matter is too low, it can cross the two lines, right?
Huh? Sorry.
For that picture in momentum space,
Yeah.
if the mass of the dark matter is too low, the two lines can cross the parabola and
The mass is too low. So meaning like you can drop this line, but like the thing that matters is not like the amplitude of this vector, right? It's this angle here. Because this angle here, let's call it theta, is equal to the velocity of dark matter. Right? So like the energy over the momentum is the velocity of dark matter, which is 10 to the minus 3. So this angle is always 10 to the minus 3. Well, this angle is 45 degrees. That's why they can never meet each other, right?
But the parabola is k squared plus m squared, right?
This is some k squared over m, right? Well, like plus m. Right? So unless you go to very non-relativistic, right? You can go all the way, then like they look similar again. But I'm here because this angle is tiny. So you cannot go all the way there. That's why like you cannot convert. Any questions? Okay, so this is the momentum space and this is the position space. Now you see why in vacuum it doesn't happen, right? So what can I do? Well, the first idea is very, very simple, right? So the problem I have is if I integrate this cosine for a very long time, like it goes to, it doesn't grow anymore. So what if I just take my detector and put it here, okay? So let's say this is my detector. I build a detector with a size that is equal to half the wavelength, right? So now like I have a half a cosine, I have a constant, the integral is non-zero now. So I'm happy, right? So that's basically the idea of the experiment called ADMX. What ADMX is, so it's one of the leading axion search experiments which look for axion photon conversion in the microwave frequencies. So really looking for a meter size waves. So the idea of the experiment is I build a cavity, right? I build a cavity and with the size which matches with the dark matter wavelengths. Now I can have all kinds of cavity mode. So if you learn Jackson, you will learn waveguide and stuff like that, right? So so this is basically a cavity, and the cavity have all kinds of TE, TM modes, right? And some of the modes will have a wave function, which is when you integrate over the volume is non-zero. So now as my dark matter is oscillating, right, it turns into one of these cavity modes. And in particular, it will turn into a cavity mode with the same frequency, right? So I will get dark matter mass. I will turn into a photon at the same frequency. And the cavity will ring it up, making the signal bigger and bigger over the coherence time. And you try to detect a small conversion of dark matter to photon. Here, like some cavity modes inside this copper cavity. I will show you a picture of the ADMX cavity towards the end. Yeah.
Does this conversion happen spontaneously? Like there's an axion inside and then for whatever reason it just became turns into a photon, or was there?
It will just simply decay to a photon. So it just convert into a photon, not decay to a photon. So here, like one thing that I haven't told you is that in order to do axion photon conversion, what I actually also need is a magnetic field. So the axion coupled to us through the axion photon coupling, which is GA gamma gamma times A. So this is a coupling constant, okay, times FF tilde. So FF tilde in like field language is basically E dot B or B dot E. So now I put a magnetic field in the background. So I apply a strong magnetic field inside this B field. Like I put this B field inside the cavity. And in the background of the strong magnetic field, the axion is going to convert into oscillating photon, which is the cavity mode.
What difference does the magnetic field make? Because if dark matter does not interact with the electromagnetic field with radiation, so why do we need the magnetic field?
So the magnetic field is what allows us to mix the photon and the axion together.
How?
Through this coupling, right, is a vertex. So in a field theory language, it's a vertex which allows you go from A to 2 photon, right? So now I put one of the photon on the background. The B field is a photon. So now like A can go into the other photon.
And this does not imply that the dark matter interacts with light.
Again, as I said many times, I never said dark matter doesn't interact with light at all. It interacts with light very, very weakly, right? And the weakness comes from the fact that this parameter is very, very tiny, right? But I never said it doesn't interact at all, right? So you never measure 0. None of the measurements tells you the interaction is exactly 0.
So wouldn't the strong magnetic field produce some virtual particles that would produce noise?
So the question is, wouldn't the strong magnetic field produce virtual particles and produce light? So if I put a constant B field, it is at 0 frequency, right? So I cannot turn in some quanta at almost 0 frequency into a quanta at higher frequencies. So now this is the difference between the absorption type signals and conversion. Because conversion, I'm looking for a signal at a particular frequency. I don't care if there are some very, very soft photons inside my cavity, as long as I can read out exactly this frequency. Okay? Good? More questions? Okay. So, so this is basically the idea behind ADMX. I'm putting a cavity in a strong magnetic field, which allows me to convert axions into a photon in a cavity mode, and then I use some receiver to read out this photon, and so if I cool the system to a really, really low temperature, making sure that I don't have any noise, and I can wait and see if a photon pop out from in the detector. And if it does, then we know we're seeing dark matter, right? So, so it's very complicated. So the concept is very simple. I will show you some real pictures, and you will see a lot of work is done by the experimentalists.
What is the expected value of the coupling constants, and how it represents the time that we need to wait on this type of cavity?
Yeah. So the constant, coupling constant. This is coming from a loop diagram. Yeah, I don't want to go into details because it's not very important. So this constant, this coupling constant, if you imagine, is where this Fa, right, as we said yesterday, is 10 to the 12 GeV. Okay, so this coupling constant is 1 over 10 to the 14 GeV. So it's really, really tiny, right? Your coupling is only a few couple order of magnitude bigger than gravity, but yet you will be able to look for something like that, which tells you how sensitive it is. Okay? All right. So that's ADMX. So from ADMX, we actually learn some special properties about this conversion type processes. So, and these two properties are somewhat related. The first property, as we know from our understanding of cavities, is cavity is only measures a particular range of frequencies, right? So most of these conversion experiment is not like a broadband. It only measures signals in a limited range of energies. So if I sending an optical photon into the cavity, it doesn't do anything, right? It only allows you to be sensitive to something which has the wavelength which is comparable to the size of the object. Okay? And the second thing, which is a related concept, is resonance. Right? Resonance. So with these cavity type experiments, we are trying to convert a dark matter into a photon that is on resonance with the cavity, so that this photon is going to be ringed up, and the signal can be enhanced, right? So I guess like if we have a glass here with a glass of water, right? Like if you sing the right tone, at some point the glass will break. But like if you sing randomly, then like the glass is going to stay there. And the reason is because the glass, it has a resonant frequency, right? If you hit the resonant frequency, the effect is much more pronounced. And here, so this is very important for our looking for waves, because the signal, as you can see from this coupling, is really, really tiny, right? So I really need everything that I can to make the signal bigger and big enough so that we can look for it. And so that's basically the concept of resonance in these wave-type detectors. Okay? So this detector, the cavity is good for meter wavelengths, right? I can build a cavity with which is a meter cubed at most, right? I can build a smaller cavity if my dark matter mass is a little bit heavier and the wavelength is a little bit smaller. But there is a limit of how much I can make it smaller and smaller, right? At some point, let's say my mass of the dark matter is order EV, right? Optical frequencies. Then you know that the corresponding wavelength is order micron, right? So I'm not going to make like a smaller and smaller cavities with the size of a micron, right? It's not very good, both because the volume is very small, so there's not much dark matter inside. Also, like making precise, like really high resonance precise devices with such a small size gets more and more complicated. So the question now becomes, are there some other ways I can change this plot, right? The first idea we had is simple. I just put a box, and so that I make them similar. Now, are there other ways I can change either the dark matter or the photon such that they look roughly the same? Okay? So who wants to do dark matter? Who wants to change dark matter? No, right? Like the dark matter is just sitting there. I cannot do anything to it. I don't know what it is, right? But photon, we know a lot of ways to change photon, right? The cavity is one of them, and there are other ways I can manipulate a photon. And that is the idea of the second experiment I will be telling you. And it's called the Lambos Experiment, where what we are trying to do is to manipulate a photon. Right? And so to do that, let's come back to this momentum space picture, right? How great it would be if I can find something which gives me a momentum, right? If I can find some object which can allow me to change the momentum of my photon, or like the quanta from dark matter to the photon, right? Can supply some momentum to the system, then I'm done, right? Then I can really convert the dark matter to a photon at the same frequency. I need something to give me a momentum kick, right? So what can give me a momentum kick? So Sonsik actually mentioned a lot of these things. In condensed matter systems, momentum are not totally necessarily conserved, right? So what are these things? Guesses? He drew a lot of these things on the board. Huh? Not rotor. Lattices, right? Okay. So if I create a lattice of a bunch of lattice sites, then there is the lattice vector, right? Usually, like if you learn from solid state physics book, then it's called G. It's the lattice vector. So momentum is not conserved up to these lattice vectors, right? I can supply some momentum if we can build a lattice of properties for the photon, right? So like most materials have lattices which are periodic structures of electron properties, electron wave functions. So can I build an object which has some lattice type properties for the photon, right? If I can do that, then I'm done. And this thing has already existed from, I guess, 300-400 years ago. And you must have learned this in high school or early in college. And this object is called anti-reflective coding, right? So what is anti-reflective coding? Is basically periodic structures of different dielectrics, right? I can have dielectrics with different refractive index, right? Optical properties of are basically in a material is basically the refractive index, right? And the lattice I create by doing periodic structures. So in this structure, I create from this periodicity, I created this lattice vector G for the photon. And in position space, what happens in this periodic structure is that the photon wave look not exactly like this, but a little bit different. So how does the photon look? Let's say I put a photon which has, like in the case of the cavity, which has this shape in this region, right? So I put the photon wave function here, like this, like in a cavity. In this part, I get a smaller amplitude. This part like this, okay? And the difference in the amplitude basically comes from the boundary conditions at this point. And you can work out how does the amplitude here and here depend on the refractive indexes, right? So, so here what we have is a half wave stack where N1 times D1 is equal to N2 times D2 equals half of the wavelength of the photon if it is in vacuum, okay? So why do I want to do that, right? So now, instead of in this picture, where this half gets some dark matter, which is totally canceled by this part, right? And this part canceled by this part. I'm not drawing very well, because like they are not exactly the same, but they cancel each other. In this case, what you can see is this, this region is a little bit bigger, and the amplitude is a little bit bigger. This region is a little bit smaller, and the amplitude is a little bit smaller. So when I do the integral of the wave function of the photon multiplied by the wave function of the dark matter, which again is a constant, now I'm not getting 0 anymore, right? So the integral between, like when you combine the yellow and the blue, is no longer 0. And that's basically the trick you can use to create a structure for the photon, such I change the property of a photon to make it similar, more and more similar to the dark matter. Right? So in the limit where like I take this refract index to infinity, I basically shrink this region to 0. I shrink this region to 0. I shrink all of this region to 0. Then I basically have a bunch of cavities on top of each other, like stacked together. And now like the signal is going as the whole volume instead of an individual one. Yeah.
How do we know that the dark matter will not refract like the light from those regions?
So how do I know like the dark matter won't reflect? Well, like if it reflected, then we have detected, right? The fact that we interacts so weakly means it doesn't do anything, right? Like any change of the dark matter property, if you can do it, then you've detected, right? Okay. Good question. Yeah.
You said that we gotta take the limit of n1 and n2 to 0.
If I take the limit where n2 to infinity. Well, like this is just like a limit, like in your mind. Like in reality, you are not really doing that. Okay. It just shows you like in that limit, like I'm basically like not having this part, not having this part, not having this part. So I'm really putting all of these cavities in series such that the signal actually grows with volume. Okay. All right. So that's the trick that we come up with. To turn a dark matter into the photon. And this idea is used in a lot of places. Again, we cannot change that dark matter. So we try to manipulate the properties of the wave we want the dark matter to convert to, such that they can do it resonantly. Right? So, so let's go back to this momentum plot. So what happens now is that just like in the case of a real material where I get band structures, in this photon material, right, or photonic crystal, which is the actual name, now you can get band structures also for the photon. Right? So you have something which is massless like the photon, and now these different waves I can create, like different waves we can create inside that structure will have different dispersion relations between omega and k. For example, this yellow one we have here is exactly this mode. Okay, so this is the mode that I'm converting to. So I can change the dielectrics properties and also like the thickness to move it up and down until at some point it matches exactly with the dark matter and the conversion happens, right? There are some other mode that exist in this structure. For example, let's say look at this mode. So what this mode is exactly the opposite, right? So I can have a mode which looks like this blue line, right? So that in each period, so in each of this section, I have half a wavelength, right? Half a wavelength, half a wavelength. But it is exactly the opposite of what we want, right? Because now this part cancels this part cancels this part. So that for the blue, the integral is 0. And you can see from this plot that you expect to be the case, right? Because this mode has energy which decreases as you increase the momentum. And that certainly is not what dark matter behaves like. And as a result, this conversion cannot happen. Right? So, so there are many other higher order modes you can use that will enable you to do some dark matter conversion. I'm not going to go into all of these details, but just to show you qualitatively that thinking about both the structure, right, in position space and momentum space, and combining them will allow you to find some structure which can manipulate the standard model wave to look like the dark matter wave and enable a conversion. Okay? Yeah.
Since we don't know the mass of dark matter exactly, to this experiment to be considered a failure, we would need to test every combination of wave.
Yeah, that's a very good question. So that is exactly the next step. Yeah. So the question is, because like so maybe like I will just provide the answer because like it's so here as you can see, like each one of these structure is only sensitive to a particular frequency or wavelength, right? In order, because we don't know what dark matter mass is, we need to go through a lot of different structures. And that's the concept of scanning, right? I need to, similarly, like in the cavity experiment, because it's a resonator, right? It also has a very narrow width in frequency that it is sensitive to, as I'm saying here, right? A resonance enhance the signal, but also reduce the range they are sensitive to. So now, in order to cover the whole frequency range, then we need to do scanning, right? You can do scanning two ways. One, I just build a lot of different structures with different properties. And we test each one of them. Each one of them is going to give me some limit. And when I combine all of them, I know that dark matter is not in this region, right? The other idea I can have is I can change as a function of distance in this way, the dark matter particle I'm sensitive to, right? So I can start with something like this, and then like I can continuously increase the separation. So this is N1, N2, N1, N2, N1, 2, N1, N2. Okay, so I'm not drawing very well, but the idea is I keep this ratio fixed, right? So I always keep this ratio fixed. But as I'm going in this direction, I can change the separation to be bigger and bigger, such that this part will be sensitive to something that is higher mass, while this part will be sensitive to a lower mass, right? Then I'm doing the scanning in this stack. And that's the idea. That's what is called a chirp stack, which allows us to be sensitive to a much wider range of masses with a single structure. Okay? So, yeah. So that's basically everything like I was telling you was how I can go and turn a dark matter to a photon, right? But we are not done yet, right? This is only half of it. The first half is signal. The second half is background. So I've got my photon coming from the stack. Let's say I'm so super lucky, the first one I try, give me a photon at the right frequency, and I know I still need to detect it, right? So and to detect it, I want to make sure that I have as little background as possible so that I actually know it is coming from dark matter. So how do I do that? Well, let's go back to this momentum plot again. So if we look at this plot, what we realize, one thing we realized is that most of the energy, this photon which is coming out from this structure gets is from the dark matter, right? This is where most of the energy of this photon comes from. But most of the momentum comes not from the dark matter, but from the lattice structure, right? And this momentum is fixed. This momentum is in the direction of the periodicity, right? So no matter if I do the regular stack or do the chirp stack, I always have the lattice momentum pointing this way, right? So, which means that the momentum of the photon is also mostly in this way. It can be go in this direction, that direction. I can put a mirror such that it only go that direction, right? So all of the photons that I'm going to get from this experiment is coming out perpendicular to the surface of the structure that I built, right? Of course, it has a small opening angle, and this angle basically comes from how much this momentum, which you get from dark matter, which is totally random, compares to the momentum you get from the stack, which is a constant, right? So what this tells you is that this angle here, which is the opening angle of the photon coming out of the stack, is also 10 to the minus 3, which is equal to the velocity of dark matter. Okay?
No, I don't get why can't I get that they should go in this direction, but why always perpendicular? Like if the dark matter that at the moment we are putting on the photon, but shouldn't it have its own moment that's pointing in other?
No, like the momentum of this photon is the g.
Only G.
It's almost only g. The small variation on top of that comes from the dark matter momentum, which is 10 to the minus 3 times the g, right? That's why like this angle is 10 to the minus 3. But most of the momentum is not from the dark matter, it's coming from the lattice structure, so it's always going that direction. Okay? So, why do I care? Well, I care because I can, if I have photons which come out perpendicular, while they are coming parallel to each other, then I can put a lens, right? You're learning optics. If I have photon coming in parallel, I can put a lens and get them focused. Okay? And how much I focus depends on the phase space. So given the fact that this opening angle is 10 to the minus 3, I can focus down to a detector which is 10 to the minus 6 in area compared to this area here, the area of this structure, right? So if I say this is a stack, which is the area of the structure, surface area, right? So this d, then a is going as d squared, right? I put a sphere stack. I put a lens. Now, like this detector can be really tiny, right? It can be basically a stack over 10 to the 6, right? As long as I can build a detector which is big enough, then I can collect all the photons. So here, I want this a stack to be as big as possible, right? Because I want to convert as many photons as I can. I want this volume to be as big as possible. So let's say like I take d equals 10 centimeter, right? Microscopic. The fact that I can reduce this by 3 order of magnitude in length and 6 order of magnitude in area means if I start with 10 centimeter squared here, I can do 100 micron squared for my detector, right? So now like my detector is super, super tiny. It helps. First, most of these very sensitive detectors, you cannot make them very big. They are expensive. You cannot erase them. The other thing is that the signal photon is coming out in parallel, perpendicular to the stack. But most of the background comes from random reactions. Now, it's not good enough if it's not like a problem if the background can hit my stack. It can hit the stack all they want, as long as they don't hit my detector, which is 6 order magnitude smaller in area or volume, right? So that's how I can reduce the background from something, I can get a signal from something this big, but only be sensitive to background, which can eventually somehow hit my very, very tiny detector. And that enhancement is what we need to make sure that the dark matter experiment is not seeing counts all the time. Okay? So that's all the magic with this experiment. Any questions? Okay. Yeah.
If they have built this, and if they detector hit once, would that be considered a dark matter detection, or how many observations?
So yeah, so the question is, let's say like I see a count. How do I know like it's dark matter, right? So that's a good question, and there are many things I can do, right? Let's say I put one detector at the focal point, and I put, let's say not many, let's 4 of them like around it. We know signal photon is only going to hit this one. It's not going to hit these 4. So if I'm seeing 50 counts here, and 1 count in each one, then I know I've seen dark matter, right? Because for background purposes, all of them are the same. The second thing, I can change my structure, right? I can go from a chirp stack to a regular stack, and the signal strength is going to change depending on the stack I build. And I know how much it will change. So now if I see a different count number, which is exactly what I predicted as I change my stack, then I know I've also seen dark matter. Okay, so that's the way that you can check. And there are many other ways you check. This is only the serious version of it. For experimentalists, they need to worry a lot more things. And I will show you some like a real picture towards the end. Okay. Good. So yeah, I have half an hour. Okay. So let's summarize a little bit. So when I do conversion, there are a few important things I need to do. The first thing that I need to be careful about is I need to build the right structure. And the first thing we understood is we need to manipulate standard model waves such that it looks like the dark matter wave, right? The second thing we need to do is we want to build something like a resonator such that I get as much signal as I can. The third thing is I need to scan, right? Such that I cover like as wider range of masses or energies as I could for dark matter, right? Because we don't know what the mass is. And the last thing, we need to use sensitive detectors and maybe some tricks such that we are not measuring background. Okay, so there are a lot of resonant detectors that has been built like in the last, well, I guess ADMX was almost 30, 40 years ago, but a lot of more things are being built, and now I will show you some pictures. Okay, let's see if it works. Did something to my computer, so.
Did you click here on?
Oh.
Should take a few seconds.
Okay. If people have questions now, like you can ask, and while we wait for this thing to go. Yeah? I don't know. I'm plugged in. Yeah, there's a saying, it takes infinite amount of theoretical physicists to figure out the projector. Oh, okay, so good. All right. Okay, so yeah, so I will show you a bunch of experiments, but like more importantly, like let's see the real plots. So this is the plot for WIMPs. We have on the y-axis the WIMP like a nucleon cross-section, which is basically how much like the WIMP scatters with us. And on the x-axis, I have the mass. The particles I was telling you mostly about is in this region here, right? But in principle, I can search the whole region between around 1 GeV to 10 TeV, okay? So as the particle becomes heavier and heavier, of course, like the density becomes smaller and smaller. So that's why like you see like all of these curves going this way. Well, if the particle is too light, then it doesn't deposit enough energy. So that's where like all of these curves have a somewhat sharp cutoff on the left-hand side. So all of these curves are different dark matter detectors. The solid ones are things that has been built and has given us results, while the dashed ones are the ones that are planned and people want to build them to cover more space, right? So a lot of these detectors, like Xenon, Wantong, LZ, actually like some of them already happened. Oops. And these detectors, as I was telling you, is made of xenon, right? So, so this is how they look like in real space. Here, like you have all the structures like that is supporting the xenon detector, and you probably know how big these things are, right? It's like human size. So this is really a giant experiment with tons of xenon like on site, right? So similarly, there are these this experiment called a CDMS, which is a little bit smaller. So it's actually like just human size for all of the structures, and then like the detectors is on the right-hand side. So the CDMS detector is made of silicon. It's like a semiconductor material. And the reason that this detector is somewhat complementary to the xenon detector is because if you go to lower and lower WIMP masses, let's say like 10 GeV, it is like when it hits the xenon, it's not like a very good, like the mass is not the same. So you want detector materials which are more like the WIMP masses, and that's why like you choose silicon. And also because we know silicon much better, we can build very precise structures, we can measure very precise signals, and it helps us reduce background as well. So you see like this is the CDMS is really something that is great at low masses, while the xenon usually cut off at much higher masses. Okay? So yesterday, someone asked about this line, which is called the neutrino floor. So on the left-hand side, we mostly have solar neutrinos, a neutrino coming from the sun. And if we want to beat that, we need to do directional experiments. On this side is even more harder. These are neutrinos coming from our atmosphere, from like cosmic rays hitting our atmosphere. And some of these neutrinos coming from supernova, some diffuse supernova background. So in this range, like we might still be able to go below the neutrino floor by a little bit, but like it will be much harder. Okay, so that's for WIMPs. So this is a similar plot for axions. So on the x-axis, we have the axion mass. Well, on the y-axis, I have the coupling that one of you asked about, J gamma gamma. So right now, like we are sensitive to something which couples with a suppression scale of 10 to the 10 GeV, and you can see how hard it is. Already, like it's a very hard, like large energy scale. But some of these cavity experiments, like the ADM experiments I was telling you about, can already get to 10 to the minus 13 and 10 to the minus 14. Okay? So these experiments are very good. So this yellow line represents the Qcd axiom. So the Qcd axiom has a very specific coupling to nucleons because it's Qcd axiom. It couples mostly to Qcd particles. It can get photon coupling through its mixing with pions and also through loops. So, but like that contribution is somewhat uncertain, which is why like for different models, this coupling can be different for Qcd axiom. And in general, it has a band, which is basically what this yellow band is. So the goal of all of these cavity experiments, which are basically different versions of this thing I was telling you about, right? It's very, very simple for series, is to cover this range here, which is the most well-motivated mass range for a Qcd axion to be dark matter. Okay? So we are, and like the one feature you can see from this experimental limit is that it's not broadband, right? It's very, very narrow in region. Some of them are really, really, really narrow. And the reason is exactly what I was telling you about. It is a resonant experiment, so it's only sensitive to a very narrow range of frequencies, and you need to scan. This is the way that ADMX is scanning, and it is trying to cover as much mass range as possible at the moment. Okay?
For how long has it been going?
So ADMX has started maybe in the 80s or like early 90s.
And there has been no detection?
There has been no detection, but like for most of the time, actually until like maybe 7 or 8 years ago, or maybe even shorter amount of time ago, ADMX was never touching the Qcd axion line because the sensitivity of the experiment is not good enough. So we keep improving the detection until I think like a couple of years ago, they finally touched the Qcd axion and then like get to the bottom of this yellow band. So it's very hard, and each scan takes some time, which is why like if you want to cover the full parameter space, you need a lot of these cavity detectors to all do their thing. And yeah, and then like you just hope like fast enough we can cover the full parameter range. Okay. So that's for axions. Here is a plot for dark photons. So the dark photon, some of you have asked me about, is similar to a photon, right? So it's a U1 particle like the photon. But it couples to us much weaker than the photon does. So the parameter epsilon tells you how much weaker it is coupling to us, coupling to the electron, for example, compared to its coupling to the photon, electron coupling to the photon. So so you see like it is more than 10 order of magnitude weaker in coupling to the electron. Than our photon, and yet now like we are sensitive to it with various experiments. Okay, so the axis again is the dark photon mass, and this is the range. So to the right of the black line is where we are most interested in searching for. So in the case of the axion, the range that is most interesting is around 10 to the minus 6 eV, which is why we need all of these cavity experiments, right, which are meter size. For dark photon, the more interesting parameter range is above this 10 to the minus 5 eV. And now, like I think, like with the new limits coming from inflation, this line has been pushed more and more towards the left. Right. So so that's why we are designing, for example, this Lamppost experiment. To look at dark photon around the EV range, and with some improvement of technology, we might be able to go to the left and hopefully like cover the full mass range. So all of these experiments again are resonant experiment. So this again is ADMX. It can be sensitive to axions, and if you just anything that is sensitive to axions, with or without the B field is also sensitive to dark photon. And all of these experiments, again, are resonant experiment. so that they can go as deep as you can, right? So this is basically the parameter space of dark photon, and we are looking for particles there too. Okay? Yeah.
Can you summarize in the previous one?
Yeah.
All these white spaces allowed, right?
Yeah, all the white spaces are allowed, and all the color spaces are already excluded. Yeah, I forgot to say that.
And the yellow
Is the prediction for Qcd Axiom.
and it's that's still allowed.
So
Except close to the red stuff.
yes. So, but like yeah, as I said, like in the lecture, well, last lecture, right? The mass that will make Qcd Axiom dark matter, 100% dark matter, is somewhere around this range. There are other production mechanisms which gives you Qcd Axiom dark matter at a little bit heavier mass from cosmic strings and cosmic domain walls. I didn't go into details about those, but roughly this is the range that people are mostly interested in. And you can see like that's why like all of the detectors are in this mass range. Right.
And so, there's so much white space. Why is some random point in the white space not well motivated? What would be wrong with something?
No, like in principle, like if I have a string theory axion, then like it can be anywhere. But we think like Qcd axion is the most well motivated. That's why we are focusing on this range here. Right. Yeah. In principle, well, like actually, like not only in principle, we are in reality we are designing experiments which tries to cover anywhere from like a 10 to the minus 11-ish EV to like tens of EV. So we want to like kill all of this white space, or maybe look for find a Qcd axion or an axion-like particle in this region, and like experimental progress is ongoing, and hopefully we'll get there sometime. Yeah, thanks. Okay. Right. So this is the ADMX detector. So there's a human here. So you can see like how big it is. Right? It's a meter-sized cavity. So, and it is a cavity which is putting a magnetic field. And then like you need to put a lot of structure around it because you want to cool it down to millikelvin temperatures. The whole thing cool down to like a couple, maybe tens of millikelvin temperatures to reduce the thermal noise, which is why it is hard and why like we are making progress slowly. But like, yeah, this is the size, and this is all the supporting structures that is needed to make this thing run, right? Okay. So one last real picture. So this one is the Lamppost Detector, which is now running at MIT and NIST, and which I designed. So here it's basically showing you the structure here, right? This is a detector, but instead of like having separated stack, which does the conversion and the lens to focus, I don't want a vibrational noise. I don't want vibrations of the system to cause my light rays to be not focusing, right? So the best thing one can do is to stick them together. So actually, we use some glue, epoxy, to like put the lens and the stack together into a structure like this, and then we put it into a metal box and connect it to a dilution refrigerator, which is both required for the photon counter to work, and also required to reduce noise. So this apparatus is now like at 10 millikelvin temperatures, and we have been running this for prototype for a couple years until now. Yeah. So that's the Lamppost detector. You can see it's tiny, right? Like it's very small. And it shows you that if you can manipulate photons in the right way, in a smart way, then you can be sensitive to, you can be very sensitive, even if you have like a small apparatus. So all the magic is there, and everyone is welcome to try. Okay? So with a few minutes left, let me make an advertisement for a school we are organizing in Perimeter. So it is a school that we are organizing on tabletop experiments. All of these experiments I was showing you that are designed to look for fundamental physics. In this lecture, I mainly told you about dark matter, but there are like many additional new phenomena you can be looking for. The particle that we are talking about, like axioms, dark photons, they don't necessarily need to be dark matter. They can also mediate forces between standard model particles. So there are fifth force experiments, equivalence principle tests that we can do to be looking for the same particle, even if they are not dark matter in our universe. So these lecturers, half of them are experimentalists, and I think 6 of them are serious, coming from like different institutions. And the idea is to have the experimentalists give serious experimental lectures, and get the serious to give experimentalists theory lectures, right? So, though like the school is geared towards mostly graduate students and postdocs, I think like most of the material will be accessible for everyone because experimentalists who they know as much theory as you do, and the theory know as much experiment as you do as well. So that's why it might be good. Of course, there will be 25 lectures, so it will go into much more advanced topics and in more details than what I have time to cover. So and it is you can register for online participation if you want. Okay.
So the event will be only online, or there will be some?
We'll have also like in-person participants on site. Yeah. Okay. So that's the school. So since I only have a minute left, let me close my lecture by showing. So this is a movie that is made about Higgs discovery. How many people have seen it? Okay. So I really like a quote from there, and I think like it's. I don't know if it is good to show you like before your exam, but the quote is this. Jumping from failure to failure with undiminished enthusiasm is the secret to success. Okay, so if you do well like in the exam, maybe I will see you in PI. If you don't, then try again. We have been trying to look for dark matter for the last 40 years. We fail it again and again, and hopefully at some point we'll succeed. And with that, that's all my lecture. Good luck.
Thank you. Okay, so we have time for questions. We are well on time.
You can also ask me about the homeworks or something.
Yeah, that's right, yeah?
Yeah. Okay.
if we find that the dark matter cannot interact with the light, what is the alternative to detect it?
So if we found out that, well, I guess if some alien tell you like dark matter doesn't interact with light, right? So what are the ways? Well, like the question is, does it interact with standard model at all, right? So actually, like many of these experiments, they don't necessarily require like dark matter to interact with light directly. If it interacts with electrons in some way or other charged particles, then the dark matter wave is going to cause oscillations of electrons, right? Or like charged particles, which will emit light. Right? So of course, like you can integrate all the electrons, then you can get dark matter light couplings from that. If you are talking about dark matter not interacting with the standard model at all, then we are in very bad position. So then like it will be very, very hard to look for it. There are gravitational effects we can be looking for. For example, with Gaia, we can ask like, does the dark matter cluster through some self-interaction? Maybe it itself has some dissipation, which allows them to form structures. And then like if we see they form structures, which and that will allow us to deduce some properties of the dark matter, right? Like if it doesn't interact at all, it's possible, but it's very unlikely because then like we don't know, like then it's very, very hard to produce them in the early universe, right? So right now, like we are looking for interactions of the dark matter, which will allow them to be produced in the early universe. In the case of the WIMP, thermal dark matter. And in the case of the axions, then like maybe they are produced gravitationally. Then like we are looking at interactions that are well motivated here. Yeah.
More questions? Let me get the mic to you.
Yeah.
It's a bit easier for us.
Yeah, it's not a question, but perhaps you could mention something about exercise 4 of your homework
Okay,
assignment.
yes, okay. So exercise 4 is a dark matter experiment that is designed. So here, like the particle we are interested in is this phi, right, scalar phi, which behaves very much like a dilaton. So it changes the strength of coupling constants in nature. So so in the problem, I say I have a coupling like this, right? So well, the standard model itself have the kinetic term of the photon with looking like this, right? So this is basically the photon, Lagrangian, and now like on top of that, I add this term, right? So what happens? What happens is now this is not the coupling constant anymore, right? The real coupling constant is a combination of this part and this part, right? So, and we know that this term I call 1 over g phi squared, which is my new fine structure constant, right? Maybe with 4 pi somewhere, but doesn't matter, okay? So what you can see from here is if I have this scalar is oscillating, right, then this term is oscillating. This is oscillating, this is oscillating. So the fine structure constant is oscillating when my scalar field is oscillating, right? So that's basically problem number 1, right? So how I can see that when I have a background scalar field is oscillating, I will have a fine structure constant which is oscillating. The second part asks what happens when the fine structure constant is oscillating, right? So here, what I'm asking you is to figure out like what type of properties will change. we talk about, yesterday or the day before, we talked about one particular case of some constant in nature changing, right? And that changes the scale measure of Pedro's weight, right? So here, again, like we are changing the fine structure constant, so a lot of other things can change. For example, hydrogen line frequencies, right? So the hydrogen line, right, has a frequency which is proportional to the fine structure constant. Now is a function of phi squared, right, times the mass of the electron, right? So now my fine structure constant is changing, then this frequency is changing, right? Genetically, for like a different atoms, right, their line structure is very, very complicated, right? You can have some like a 4F to, now I'm just making things up, like a 3D transition, right? So that transition have a different dependence on fine structure constant. So naively, the transition will depend on fine structure constant to 2 plus some other number, right? And that number is some order 1 number, which tells you about the particular properties of this transition. So the reason we want to do that, think about that is because I cannot really measure a frequency, right? Frequency has units, so I must be comparing it with another thing that has a unit, right? So here, what I'm trying to do is I'm trying to say, now I have the frequency of strontium, right, and the frequency of ytterbium. So let's say call this a number kappa. Then I will have a kappa for strontium and a kappa for ytterbium. So I can do, if I take this ratio, then I'm sensitive to alpha to the kappa strontium minus kappa ytterbium, right? Okay? And now this is a function of phi, right? So I can do, like a phi is a really tiny perturbation, so I can do some Fourier, like a Taylor expansion. So this is proportional to kappa strontium minus kappa ytterbium phi, right? Which is a function of time, right? So now what happened? So what happens now is that this ratio between the frequencies is oscillating as a function of time, right? So atomic clocks is basically using these frequencies or the inverse frequencies to measure time, right? So we probably heard about the Cdm clock, and a second is defined as 9 million blah 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 blah, a bunch of number time periods of Cdm oscillation, right? So here, like atomic clock, basically is measuring these frequencies to set an absolute size of time. I don't want an absolute value for time. I just want this frequency ratio. And if I can measure this frequency ratio to a very high precision, which atomic clocks do, then I'm sensitive to really, really tiny perturbations of this phi, right? So that's basically the idea behind the number 2. And number 3 and number 4 are just some mathematics you can do to figure out how big is the amplitude of phi, right? So the one thing you need to remember is the density of the scalar field is the mass squared, or the frequency squared times the amplitude squared, right? So from the density around, like of dark matter, and the mass of the particle, right? You can know what is the amplitude of phi. And then you can, from like this measurement, you know about what is the size of this ratio, right? So, sorry, Fi, right? You know what is the size of this ratio, and as a result, you know what is the scale. Okay, so that's basically the homework problem.
Sorry, what was kappa again?
Kappa is a constant which tells you like how does different atomic transition depends on the fine structure constant. For hydrogen, the simplest one, like kappa equals 0. It goes as alpha squared. But like for more complicated transitions, you have different cancellations, Like you need to go through like a bunch of, the wave functions are overlapping with each other, right? So this constant is usually non-zero.
Typically, it's some integer.
No, it's like some random number. Like it can be like point, I think like for aluminum, it's like 0.008. And for ytterbium, I think it's 2.7. And for strontium, like it's maybe 3 point something or something. I don't exactly remember all of them, but like they are all like order 1 numbers that are somewhat random. And you can compute them exactly in atomic physics. Yeah.
Does this experiment have been done?
Yeah, so doing this experiment is hard. I didn't put in like a plot for the atomic clock. Each atomic clock is roughly the size of this thing. Okay, like the whole room. It's like it's not like a tiny clock. You shouldn't think of that. So like most of the most sensitive clock is in NIST in Colorado. And they don't have 2 clocks, I think. I think they probably still don't have 2 clocks in the same building. So comparing them is hard. There are similar experiments which were already done and place constraint based on this proposal on like this coupling. And you can do actually very, very well compare like it.
If this were true, then would we have a problem in our definition of seconds? Because throughout the history of the universe, it would have different values compared to now.
So yeah, like the second will, yeah. So like the question is like we will have a problem of the definition of second. I mean like right now like we are at a precision, right? Like for these clocks of 10 to the minus 18. So we're like and the measure like the oscillation we are measuring is really like a fractional change, which at that level. For all your like everyday life purposes, it doesn't really matter, right? I'm not like getting to launch at exactly a time like to that precision. Yeah.
Could we expect maybe a relation between sterile neutrinos and dark matter at all?
So the question is, do we? But actually, like maybe before I answer, so like to close this part, you will find that like this value f phi, if you do the homework, to be much bigger than Planck, meaning that you are sensitive to some particle which is coupling weaker to us than gravity with this thing, and that's why I would say like the clock is really, really powerful. So so going back to the question was, do we expect some relation between stellar neutrino and dark matter? Well, I think like people really thought like stellar neutrino could be dark matter, and there are models which predict a particular mass for that stellar neutrino so that it can be dark matter in our universe. That scenario has already been excluded. So now you can add like more ingredients to your model such that maybe it is still stay above water, but it gets into ugly multi-billion territories. Yeah. Okay. More?
Any other questions?
Well, nice. First of all, thank you for the lectures.
Thank you.
I just wanted to say something, which is Yumba, and that's it. Nice.
Okay. I don't know what that is. Yeah, 6.
Okay.
Okay.
And if there's also some bets, you probably won. Yeah. Okay. If there are no more questions, let's thank Junwu once more. And we come back at 2, as usual.
What is that? No. Okay. No, understand. Sorry. Cool. Okay.
Very good. Thank you.
No, thank you. Yeah, just pay. been amazing.